Hello and welcome to today's session on probability distribution types. I am Dr. Maruf Ahmed Mir, PhD in Financial Markets and MBA in Finance and Accounts from AMU Aligarh. And at present, I am associated with Asian Business School, Noida as Associate Professor in the area of Finance and Accounts. Dear students, let's start with understanding the probability distribution. In probability theory and statistics, a probability distribution is the mathematical function that gives the probabilities of occurrence of different possible outcomes for an experiment. It is the mathematical description of a random phenomenon in terms of its sample space and the probabilities of events, that is, subsets of the sample space. A probability distribution is a statistical function that describes all the possible values and likelihoods that a random variable can take within a given range. This range will be bounded between the minimum and the maximum possible values, but precisely where the possible value is likely to be plotted on the probability distribution depends on a number of factors. Now, these factors include the distribution's mean, which is average, standard deviation, skewness, and kurtosis. Perhaps the most common probability distribution is the normal distribution or the bell curve, although several distributions exist that are commonly used. Typically, the data generating process of some phenomenon will dictate its probability distribution. This process is called the probability density function. Probability distribution can also be used to create cumulative distribution functions, which adds up the probability of occurrences cumulatively and will always start at 0 and end at 100%. Academicians, financial analysts, and fund managers alike may determine a particular stock's probability distribution to evaluate the possible expected returns that the stock may yield in the future. The stock's history of returns, which can be measured from any time interval, will likely be composed of only a fraction of the stock's returns, which will subject the analyst to sampling error. By increasing the sampling size, this error may be dramatically reduced. Conditions of probability distribution. X and P probability of X is said to be constitute a probability distribution if X is a random variable. Number 2, the probability of X is greater than 0. Number 3, sum of probability is equal to 1. To know about probability distribution, you must know about variables and a random variable. A variable is a symbol, say A, B, X, Y, etc. It takes any of the specific set of values. In a statistical experiment, a random variable is the value of a variable. Usually, a capital letter denotes a random variable and a lowercase letter denotes one of its values. For example, the capital X denotes the random variable X, probability of X denotes the probability of X. Now, P of X equal to small x is the probability that the random variable X is equal to a particular value denoted by small x. For example, P of X equal to 1 is the probability that a random variable X is equal to 1. Types of probability distributions. Statisticians divided probability distribution into following types. One is discrete probability distribution, second one is continuous probability distribution. Now, discrete probability distribution. Discrete probability functions are the probability of mass functions. It assumes a discrete number of values. For example, when you toss a coin, then counts of events are discrete functions because there are no in between values. You have only heads or tails in a coin toss. Similarly, when counting the number of books borrowed per hour at a library, you can count 31 or 32 books and nothing in between. Now, types of discrete probability distributions. Binomial distribution. A Bernoulli distribution has only two outcomes, 1 or 0. Therefore, the random variable x takes the value 1 with the probability of success as p and the value 0 with the probability of failure as q, or 1 minus p. Thus, if we toss a coin, the occurrence of head denotes success and a tail denotes failure. The probability function is px in bracket 1 minus p bracket close 1 minus x, where x has subset 0 and 1. Normal distributions. Normal distributions are for the most basic situations. It has the following characteristics. Number 1, mean, median and mode coincide. Number 2, the distribution curve is bell shaped. Number 3, the distribution curve is symmetric along x equal to mu. Number 4, the area under the curve is 1. Next is Poisson distribution. Counting number of books at a library falls under probability distribution. Poisson distributions have the following assumptions. First, a successful event is not influencing the outcome of another successful event. Number 2, the probability of success over short duration equals the probability of success over a long duration. Next, the probability of success in a duration nears 0 as the duration becomes smaller. Continuous probability distribution. It is also known as the probability density function. There is a continuous distribution if the variable assumes to have an infinite number of values between any two values. Continuous variables are measured on scale like height, weight and temperature. Now, when compared to discrete probability distributions where every value has a non-zero outcome, continuous distributions have a 0 probability for specific functions. For example, the probability is 0 when measuring a temperature that is exactly 40 degrees. Types of continuous probability distributions. Number 1 is uniform distributions. When rolling a dice, the outcomes are 1 to 6. The probabilities of these outcomes are equal, and that is a uniform distribution. Suppose the random variable x assumes k different values. Also, p into x equal to x into k is a constant. The p bracket x equal to x into k is equal to 1 by k. Cumulative probability distribution. When the probability that the value of a random variable x is within a specific range, cumulative probability comes into the picture. Random variables. A random variable is random if it takes on different values as a result of the outcomes of a random experiment. A random variable can be either discrete or continuous. If a random variable is allowed to take on only a limited number of values which can be listed, it is discrete random variable. On the other hand, if it is allowed to assume any value within a given range, it is a continuous random variable. You can think of a random variable as a value or magnitude that changes from occurrence to occurrence in no predictable sequence. A cancer screening clinic, for example, has no way of knowing exactly how many patients will be screened on any one day. So, tomorrow's number of patients is a random number. The value of a random variable are the numerical values corresponding to each possible outcome of the random experiment. If past daily records of a clinic indicates that the values of the random variable range from 100 to 115 patients daily, the random variable is a discrete random variable. Now, table 1 illustrates the number of times each level has been reached during the last 100 days. Note that the table gives a frequency distribution. To the extent that we believe that the experiment of the past 100 days has been typical, we can use this historical record to assign a probability to each possible number of patients and find the probability distribution. Let's understand now creating a probability distribution. Now, we have accomplished this in the table on the screen by normalizing the observed frequency distribution. In this case, dividing each value in the right hand column of the table by 100, the total number of days for which the record has been kept. The probability distribution for the random variable daily number screened is illustrated graphically in the figure. Notice that the probability distribution for a random variable provides a probability for each possible value, and that these possibilities must sum to 1. Table shows that both these requirements have been met. Furthermore, both table and figure give us information about the long run frequency of occurrence of daily patient screening we would expect to observe if these random experiments were repeated. The expected value of a random variable. Suppose you toss a coin 10 times and get 7 heads like this: heads 7, tails 3, total 10. Strange. You then ask a friend to try tossing the coin 20 times. She gets 15 heads and 5 tails. So now you have in all 22 heads and 8 tails out of 30 tosses. Daily number of women screened. Probability distribution for the discrete random variable daily number screened. What did you expect? Was it something closer to 15 heads and 15 tails, half and half? Now, suppose you turn the tossing over a machine and get 792 heads and 208 tails out of 1000 tosses of the same coin. You might now be suspicious of the coin because it didn't live up to what you expected. Expected value is the fundamental idea in the study of probability distribution. For many years, the concept has been put to considerable practice used by the insurance industry. And in the last 40 years, it has been widely used by many others who must take decisions under conditions of uncertainty. Calculating the expected value. To obtain the expected value of a discrete random variable, we multiply each value that the random variable can assume by the probability of occurrence of that value and then sum these products. Table 3 illustrates this procedure for our clinic problem. The total in the table tells us that the expected value of a discrete random variable number screened is 108.02 women. What does this mean? It means that over a long period of time, the number of daily screenings should be average about 108.02. Remember that the expected value of 108.02 does not mean that tomorrow exactly 108.02 women will visit the clinic. The clinic director would base her decisions on the expected values of daily screenings, because the expected value is a weighted average of the outcomes she expected in the future. Expected value weights each possible outcome by the frequency with which it is expected to occur. Thus, more common occurrences are given more weight than the less common ones. As conditions change over the time, the director would recompute the expected value of daily screenings and use this new figure as the basis for decision making. In our clinic example, the director used past patients' records as the basis for calculating the expected value of daily screening. The expected value can also be derived from the director's subjective assessment of the probabilities that the random variable will take on certain values. In that case, the expected value represents nothing more than her personal convictions about the possible outcomes. Deriving expected value subjectively. In this section, we have worked with the probability distribution of a random variable in the tabular form. and in graphical form. In many situations, however, we may find it more convenient in terms of the computations that must be done to represent the probability distribution of a random variable in algebraic form. By doing this, we can make probability calculations by substituting numerical values directly into an algebraic formula. In the following section, we shall illustrate some situations in which this is appropriate and the methods for accomplishing it. The binomial distribution. One widely used probability distribution of a discrete random variable is the binomial distribution. It describes a variety of processes of interest to managers. The binomial distribution describes discrete, not continuous data resulting from an experiment known as Bernoulli process, after the 17th century Swiss mathematician Jacob Bernoulli. The tossing of a fair coin a fixed number of times is a Bernoulli process, and the outcomes of such tosses can be represented by the binomial probability distribution. The success or failure of interviews of an aptitude test may also be described by a Bernoulli process. On the other hand, the frequency distribution of the lives of fluorescent lights in a factory could be measured on a continuous scale of hours and would not qualify as a binomial distribution. Use of Bernoulli process. We can use the outcomes of a fixed number of tosses of a fair coin as an example of a Bernoulli process. We can describe this process as follows. Number 1. Each trial, each toss in this case has only two possible outcomes: heads or tails, yes or no, success or failure. Number 2. The probability of the outcome of any trial, that is toss, remains fixed over time. With a fair coin, the probability of heads remains 0.5 each toss, regardless of the number of times the coin is tossed. Number 3. The trials are statistically independent. That is, the outcomes of the toss does not affect the outcome of any other toss. Each Bernoulli process has its own characteristic probability. Take the situation in which historically 7/10 of all people who applied for a particular type of job passed the job test. We would say that the characteristic probability here is 0.7. But we could describe our testing results as Bernoulli only if we felt certain that the proportion of those passing the test, 0.7, remains constant over time. The other characteristics of the Bernoulli process would also have to be met. Of course, each test would have only two outcomes, success or failure, and the result of each test would have to be statistically independent. In more formal language, the symbol P represents the probability of a success, in our example 0.7, and the symbol Q, which is equal to 1 minus P, the probability of failure, which is 0.3. To represent a certain number of successes, we will use the symbol R, and to symbolize the total number of trials, we will use the symbol N. In the situation we will be discussing, the number of trials is fixed before the experiment is begun. Using this language, in a simple problem, we can calculate the chances of getting exactly 2 heads in any order on 3 tosses of a fair coin. Symbolically, we express the value as follows: P equal to characteristic probability or probability of success equal to 0.5. Q will be equal to 1 minus P, probability of failure, which is equal to 0.5. R will be number of successes desired, which is equal to 2. N will be number of trials undertaken, which is equal to 3. Next is Poisson distribution. There are many discrete probability distributions, but our discussion will focus on only 2: the binomial, which we have just concluded, and the Poisson, which is the subject of this section. The Poisson distribution is named for Simeon Denis Poisson, 1781-1840, a French mathematician who developed the distribution from studies during the later part of his lifetime. The Poisson distribution is used to describe a number of processes, including the distribution of telephone calls going through a switchboard system, the demands, needs of patients for the service at a healthcare institution, the arrival of trucks and cars at a toll booth, and the number of accidents at an intersection. These examples all have a common element. They can be described by a discrete random variable that takes on integer whole values like 0, 1, 2, 3, 4, 5 and so on. The number of patients who arrive at a physician's office in a given interval of time will be 0, 1, 2, 3, 4, 5 and some other whole number. Similarly, if you count the number of cars arriving at a toll booth on the New Jersey Turnpike during some 10-minute period, the number will be 0, 1, 2, 3, 4, 5 and so on. Characteristics of processes that produce a Poisson probability distribution. The number of vehicles passing through a single turnpike toll booth at thrust hour serves as an illustration of the Poisson distribution. Characteristics. Number 1. The average mean number of vehicles that arrive per rush hour can be estimated from the past traffic data. Number 2. If we divide the rush hour into periods, intervals of 1 second each, we will find these statements to be true. A. The probability that exactly one vehicle will arrive at a single booth per second is a very small number and is constant for every 1 second interval. B. The probability that two or more vehicles will arrive within 1 second interval is so small that we can assign it as 0 value. C. The number of vehicles that arrive in a given 1 second interval is independent of the time at which that 1 second interval occurs during the rush hour. D. The number of arrivals in any 1 second interval is not dependent on the number of arrivals in any other 1 second interval. Now we can generalize from these 4 conditions described for our toll booth example and apply them to other processes. If these new processes meet the same 4 conditions, then we use a Poisson probability distribution to describe them. In Poisson distribution, we observe only the occurrence of the events. So, in the case of Poisson distribution, we are simply concerned with the count only the happening of the event, unlike the binomial distribution where we are concerned with both the happenings, success as well as non-happenings, failure of the event. That is all for today. Hope you have understood. So, we will meet in the next episode with a new topic. Till then, take care. Goodbye.